So here I'm talking today about exoplanets or finding life in the galaxy. So here's actually a picture of little Rob on the right, meeting one of his heroes, an astronaut. I routinely get asked if I ever wanted to be an astronaut as a little kid, and the answer is a firm no, because I'm definitely afraid of heights. So what I think is the next best thing, which is an exoplanet astronomer. Let's unpack what this means exactly. So exoplanet, that's short for extrasolar planet. And extrasolar literally means anything beyond our own solar system. And then planet, hopefully you guys all know what that means. That's a planet. So an exoplanet is any planet outside of our solar system. An exoplanet doesn't necessarily have to be orbiting another star outside of our solar system. There's actually free-floating exoplanets that originally formed around stars and then were eventually ejected out of their solar system due to gravitational dynamical interactions. So generically, an exoplanet is any planet outside of our own solar system. And I'm an astronomer, and I think all of you know what that is. That's someone who stares at the sky, or more likely their computer, for way too long. So I work at NASA's Jet Propulsion Laboratory, operated also by Caltech. I go to Palomar Observatory a lot, and it's absolutely my favorite observatory to ever go to. I've been to a few, so I love Palomar. I'm sad I won't be able to go there in person for a while. But what I'm doing at JPL is I'm trying to answer one of the age-old questions, is, are we alone in the universe? And answering this question is what I get to do daily, which is a lot of fun. But before we sort of look to where we want to be going, to discovering life elsewhere in the universe, it's always helpful to look back at where we came from. Also, I'm married to a historian, so if I don't talk a little bit about history, she will, I'll get in trouble tonight later on when she hears about that. So quick bit about history. Giordano Bruno, he's that guy on the right. He was a 16th century philosopher who postulated that that planets outside of our own solar system existed. And it's really interesting that exoplanet astronomy, even though it's one of the youngest fields in astronomy, it's only about 20 to 30 years old. The idea of looking for life outside of our own solar system is something that's been around for hundreds of years. Isaac Newton, he's of course the inventor of fig Newtons. He said in his book Principia, where he discussed the theory of gravity, said, and if the fixed stars are the centers of similar systems, they will all be constructed to a similar design. In other words, just like we have 8 planets orbiting our own sun, 8 because Pluto's not a planet, 8 planets orbiting our own sun, it stands to reason that if you were to go out into the night sky and you see the 6 stars that you can see from LA, or hopefully more where you guys are, that those stars potentially and likely have their own planets or orbiting around them. And potentially some of those planets might actually have life that's looking back at our own star's light. And we know that these 2 dead guys are absolutely correct. In the last 20, 30 years, we've been discovering more and more exoplanets. And as we know where to look, how to look, as technology gets better, as our telescopes get better, and our data reduction methods get better, we are discovering more and more exoplanets. This is exponentially increasing. And we now know today that on average, there are as many exoplanets as there are stars. And when there's lots of planets, there's likely potentially life. So the question is, how do we go and how do we discover life on these planets? Well, it's basically a 3-step method, right? First, you have to find an exoplanet. So the question is, how do we find them? There's actually a bunch of different ways that we can find exoplanets. The 3 methods I'll be focusing on today are the radial velocity, transit, and direct imaging methods, because arguably we know the most about exoplanets from these 3 methods. So the radial velocity method, let's look at that in detail. So this is also sometimes called the Doppler shift or the Doppler method. And what this does is this measures the wobble of a star as a planet orbits the star. And as that planet, as the star is gravitationally tugging on the planet, causing the planet to orbit around the star, but the planet itself is also gravitationally tugging its host star. And what that does is the planet actually causes the star to wobble back and forth. And if we look at the spectrum of that star, basically the rainbow of that star, we can actually watch the light of the star blue shift as it gets towards us and red shift as it moves farther away from us. So this directly allows us to measure the wobble of the star. And by looking at the wobble of the star, we can infer the existence of an exoplanet. But this only gives us motion along our line of sight. We're only going to see a Doppler shift where the object is moving towards us or away from us. If it's perpendicular to our line of sight, that motion and that Doppler shift will also be perpendicular to us, and we won't see it as a Doppler shift. But very importantly, the radial velocity method gives us the planet's mass, because the bigger the planet, the bigger the wobble. So this allows us to actually directly weigh the planets by how much they gravitationally tug their host star back and forth. So again, the advantages of this method is it gives us the mass of the planet. However, the disadvantages is that we're biased towards large planets in short period orbits. In other words, it's easier to find large planets because they're tugging on their star more often. It's also easier to find planets that are orbiting around their star very frequently because that's less of a baseline we need to look for that signal. So if we wanted to look for small planets such as Earth-sized planets, in Earth-sized orbits, orbiting around a solar-type star, planets that we think have the conditions that are conducive to life, we need large telescopes, such as NASA's and the 10-meter Keck telescope, which I'm showing a photo of there at the top right. Another method that's actually very near and dear to my heart, because I use this a lot, and this is the method I personally specialize in, is the transit method. So if we're looking at a star, and that star has a planet orbiting around it, if we're lucky and the geometry lines up, that planet can pass in front of its host star, blocking out the star's light. And the planet literally casts a shadow all the way back on the Earth. And when the planet passes in front of its host star, it causes the host star's brightness to dim just a little bit. And that dimming of the host star tells us directly how big the planet is in radius compared to its host star. So you can actually back up the ratio of the area of the planet relative to the area of its host star. And this method can actually be very difficult to see. At best, the dip in brightness is roughly about 1 to 3%. But this method allows us to study the atmosphere of an exoplanet by observing how the planet's atmosphere absorbs the light from the host star. We can then infer the composition of these exoplanets. And the transit method has been used with great success. It's been used to discover 3,000 of the currently 4,000 currently known exoplanets. So some advantages of the transit method is that it's actually can be relatively cheap. There's amateur astronomers that are routinely using 6-inch, 4-inch telescopes to look at transits almost every single night. I saw a post online where someone took a regular DSLR camera and made a relatively cheap mount and actually was able to observe a transiting exoplanet. Another advantage is that this gives us the size of the exoplanet relative to its host star. But just like the radial velocity method, we're biased towards large planets in short period orbits because the bigger the planet, the bigger the dip in the light curve, or the bigger the dip in the star's brightness. The smaller the planet, the smaller the dip. Also, we can have false detections, stellar activity, or eclipsing binaries can also sometimes look like transit events. And you also need that geometry as well, because if the planet's orbiting perpendicular to our line of sight, we'll never block out its star's light and we'll miss that transit completely. So the transit method's been used, for example, to great success by NASA's KEPLER and K2 mission. This is a NASA Planet Hunter that was launched in 2009. It discovered over 2,000 confirmed exoplanets, and there's another potentially 4,500 that are candidates. And what Kepler did is it looked at this small portion of the sky at the top right, and it's a field of view that's roughly the size of the moon, and it's towards Cygnus the Swan. And in this small field of view, Kepler discovered thousands of exoplanets. So if we take that small field and we extrapolate it to the entire sky, it is the Kepler mission that told us the ubiquity, the frequency of planets in our own universe, that planets are numerous, they're everywhere, and they're likely. And with lots of planets, there also might mean more life, which is pretty exciting. So if we look at the number of planets that have been discovered by year, these two big jumps in 2015 and 2016 were two large data releases by the Kepler mission, where they published over 1,000 exoplanets on both. So unfortunately, Kepler's reaction wheels failed, and Kepler has officially been retired. But about a year or two ago, NASA launched a mission called TESS, which is the Transiting Exoplanet Survey Telescope. So TESS is actually, instead of focusing on one small part of the sky, is actually doing a full sky survey. And TESS is very crucial because it'll discover at least 1,000 planets, but some estimate that it'll be discovering up to 10,000 plus. So today we know of about 3,000 to 4,000 exoplanets. TESS will add another 10,000 transiting exoplanets to our current database. And this is crucial because transits are used today by a few missions, and they will be used by future missions to characterize exoplanets. So HUBBLE, the Hubble Space Telescope, for example, has studied the atmospheres of transiting exoplanets on the order of about 40 to 50 of them. The James Webb Space Telescope is predicted to look at in great detail and great precision the atmospheres of tens to maybe even 100 or 200 exoplanets. Ariel, which is a mission launched by the European Space Agency, which will be launched in 2028, will be looking at hundreds to 1,000 exoplanets. And then the next generation missions, an Astro 2020 mission, which are missions that are explicitly designed to look for life on these planets. They might be looking at, they'll likely be using the transit method as well to observe and to characterize the atmospheres of potentially habitable exoplanets. But in order to observe a transit, we have to know exactly when that transit occurs. So this requires very precise timing. So for example, if I write a Hubble Space Telescope proposal and I want to observe a transit, let's say I look up on an archive and I look up the transit time and I predict it to occur in red there. But let's say the transit actually comes a little bit earlier due to uncertainties in the measurements. Well, I run the risk of partially or completely missing that transit. And wasting time on a precious resource such as Hubble or James Webb is definitely a thing you do not want to do, because it actually prevents us from then doing other interesting science cases, whether that's more transit observations or, for example, looking into what's the source in dark energy and dark matter, for example. So knowing very accurately that precise transit time is very, very important to maximize the efficiency of these very precious resources, these space-based telescopes, and also large ground-based observatories. But this is actually where small telescopes can help out directly. So small telescopes, as I mentioned before, are actually capable of observing these transiting exoplanets. So on the right is a sample light curve. As you can see, we're observing an exoplanetary system called HAP-P32b. And when the planet passes in front of its star, it causes the stars to dip in brightness about 2.5%. And this data set was actually taken with a 6-inch telescope, and the host star was relatively dim, about 11.289 Vmax. So despite this being a relatively small telescope, despite this being a comparatively dim star, despite not even having perfect tracking, the star actually wandered across the focal plane by about 300 pixels. We're still able to get very high precision measurements and light curves, as I'm showing there on the right. So this relevation, this data set really made us think, okay, if we can get really precise data from a small telescope, what can the amateur astronomer community do, for example, to aid and help out with maintaining and operating these large telescopes with higher efficiency? So actually what we did is we did a study on utilizing small telescopes operated by citizen scientists for transiting exoplanet follow-up. And we studied in depth what small telescopes can do to help out larger telescopes. And this is a really cool study that we published just a few months ago. So here's the usual suspects of quote-unquote professional astronomers, those of us who are lucky enough to get paid to study astronomy. and also 2 of my interns made it to the paper as well. What's really exciting and cool for me is that we also had a bunch of citizen scientists and amateur astronomers that joined our study as well. You'll notice these 2 suspects, Bob Massey and Scott Dixon, are actually docents there at Palomar Observatory. So thank you guys for your help on this paper. It was really crucial in their contribution to getting this paper published. They actually gave us some sample data and allowed us to publish it in this publication, which was really awesome. Also, we had for this paper contributions from high school students. Kalei Tak, who is a teacher at the Stanford Online High School, actually has some really awesome high schoolers, Conley Ball, Sujay Nair, and Quinn Perrion, who have been very active in our collaboration in reducing transiting exoplanet data from small telescopes. And Kalei actually is starting to teach classes about observing transits of small telescopes, which is really exciting. So this science that we were able to calculate that we discovered that small telescopes can make meaningful contributions and very crucial contributions to large observatories, both in the space and also on the ground, made us sort of think about launching a new project called EXOPLANET Watch. And EXOPLANET Watch is a citizen science project that allows people to make their own transit observations and actually help use large telescopes more efficiently. So the user experience on EXOPLANET Watch is that first step is you plan. So we actually have our own website. You can just Google NASA EXOPLANET Watch and it should pop up right there in your browser. We actually identify for our users targets every single night for each of the US time zones. And these are high priority targets. However, you are more than welcome to observe any target you want. So in that middle panel, that's the Swarthmore Transit Finder. The bottom panel is the NASA Exoplanet Archive, which also has a transit planner. So you pick a transit or an object that makes sense for you for your location, and then you go out and you observe it. So right here in the background is actually a photo taken by one of our citizen scientists, amateur astronomers, Doug Lalla, where he actually observed the transit of an exoplanet called HD 189733b, which is indicated by that arrow at the bottom. But also the Dumbbell Nebula happens to be nearby. So Doug was actually able to get transit data at the same time as making a really great photo of the Dumbbell Nebula. Then once you do your own observations with your own telescope, you reduce your own data, and you are more than welcome to use any data reduction package that you want. We actually have our own data reduction package called Exotic, which I'll be talking a little bit more about in a second. And Doug actually used Exotic to reduce his observations of HD 189, and there's his light curve at the very bottom. Then you upload your data and your observations to the AAVSO's Exoplanet database. And so as long as your data is in the right format to be accepted by the database, it doesn't matter what data reduction tool you use. If you love AstroImageJ, if you've used HOPS before, you can use Exotic. It's up to you. As long as it's in that right format, that's all that matters at the end of the day. Then once you upload your data, then you can publish your own results, or also look at the archive at the AAVSO, the database, to publish results as you wish. And one interesting facet of EXOPLANET Watch is if someone else uses your data in a publication, they'll be required to reach out to you through the AAVSO as an intermediary to see if you would be interested in being a co-author on a paper. Because if you're doing the work, you deserve the credit anyways. And then what happens at JPL is we actually have an automated data reduction pipeline called CITISENS, which is the Citizen Initiated Transit Information Survey Enabling NASA Science. And what this pipeline does is it automatically scrapes every single day the AVSO database. It downloads all that data, and then we process it locally behind the JPL firewall, and then we publish it immediately to our website. So therefore, amateur astronomers, but also professional astronomers can go to our website, which will be launching in September officially, and get those data products and do whatever they want. If it's as simple as planning an observation, that's great. Alternatively, since all of our data products will be immediately available online, they can use those data to also write their own papers and publications, as well as any of you if you're interested in doing so. We just ask that you just cite our paper, give us a little acknowledgement, and also if you use any amateur astronomer data, that you reach out to them and offer to add them as co-authors on your paper. So I mentioned EXOTIC before. This is actually our own in-house data reduction tool. It stands for the Exoplanet Transit Interpretation Code. And what EXOTIC does is it takes your raw FITS files and fully performs multi-object photometry on them. It automatically picks up the best comparison star. It automatically fits for air mass variations. It also automatically fits your data using a very statistically robust fitting algorithm. And it produces that scientific grade light curves. So that one at the bottom right, that's HAPI-32. This is actually a direct output from EXOTIC, and I was able to just copy and paste it into this paper, which is pretty cool. It also generates, just like AIJ, sort of a field of view of your target and your comparison star. Another cool feature of EXOTIC is that it actually has a real-time data reduction feature. So let's pretend you're, for example, at a star party for when we can start gathering together again, hopefully very soon. And when you're observing a transit, it's actually really boring observations. This is one thing we joke about. If when you're doing a transit, especially at Palomar, boring is good because that means everything is going well. But for a transit, you just slew to your star and you sit on it, you just take lots of exposures. Observing transits is actually much easier than astrophotography. So if you are fine with astrophotography, you should be able to do transit observations easy peasy. But when you're observing a transit, you're observing a star and you're waiting for that planet to pass in front of the star, and the star only dims about 1%. So that's not really cool to look at by your eye. So what we did is we coded up this automatic and real-time data reduction method. So you can point to your screen during a star party and point out to the public, look, we're actually observing a planet orbiting around a star, you know, hundreds of light years away, which I thought was pretty cool. You can actually download it right now for free. It runs on Mac, Windows, and Linux computers, or Unix computers. You can download it at that GitHub address at the bottom left. It's also linked directly from our website. So we actually need all of you right now to help us observe any exoplanet, but particularly the ones we've prioritized on our website, and upload your results to the AVSO's exoplanet database. If you don't have a telescope, no problem. We're actually working on a framework to give archival data to some of our users, those who don't have a telescope and or a camera, to reduce. We need your help to help us test out the EXOTIC reduction code. And we actually have, this is actually a great opportunity because your input we're taking very seriously, and your input will help us make EXOTIC more user-friendly. So if there's a feature that you would like, or a tool you'd like, or if something is not as friendly as you'd like, you can let us know and we will definitely address your concerns and comments. Our official launch is probably mid to end September. You can contact us if you want to participate in this project by emailing us at exoplanetwatch@nasa.jpl.gov, or you can visit our website, exoplanets.nasa.gov/exoplanet-watch. All right, I'll get off my soapbox now. And so we've talked about in detail the radial velocity method and the transit method. Radial velocity gives us the mass of these planets. The transit method gives us the radius of these exoplanets. So the next question now is, how do we find, the next other method we use is the direct imaging method. And just as the name implies, this is taking photographs of exoplanets. However, there's actually a big problem. If you want to take an image of an exoplanet, the star actually gets in the way. So the question is, how do you block out the light from that star in order to resolve the light emitted or reflected by the exoplanet? So let's do a little thought experiment. Let's say we have a sun-like star and we take something that's easier to see, like a large planet that's really hot, like a hot exo-Jupiter. Well, if you wanted to look at that light from that large, very warm planet, that's like looking for the light of a firefly flying around a lighthouse and you're about a mile away, because the light emitted from that hot exo-Jupiter is 1,000,000 times fainter than its host star. Now let's make it a little bit harder. We want to find life around on exoplanets, so we want to look for Earth-like exoplanets. However, an Earth-like exoplanet is 10 billion times fainter than its host star. So that's like looking from the light emitted from one bioluminescent alga also around that same lighthouse. So it's a very big problem. How do you block out the star so you can resolve the light from the planet? And this is where the direct imaging method comes into play. So those of you who saw the transit or the solar eclipse a few years ago, remember when the moon went in front of the sun, you could see the corona. You could also see nearby host star or nearby stars when the moon blocked out the star's light. So if we devise an instrument that can simulate an eclipse that blocks out the star's light, it allows us to resolve and uncover the light from the planet orbiting around that host star. So I have this quick video on how to image exoplanets. I'm going to share my sound as well. 1 second. And while this is playing, I'm going to go grab some more water. So I'll be right back. 1 quick second while this plays.
A coronagraph is a way to see distant planets hidden by the glare of the star they orbit. The coronagraph reduces the light coming directly from the star to separate it from the light reflected by the planet. WFIRST doesn't block the star's light with an opaque disk as a simple coronagraph might. Instead, it uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light, effectively making it disappear, while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. Collecting more light increases the image signal, but the planets are still hidden under blobs of leftover, distorted starlight. To remove these blobs, the coronagraph has special deformable mirrors that can change shape by using hundreds of tiny pistons. This corrects the distortions in the light beam. As the mirrors deform, the blobs of light slowly begin to disappear, revealing brighter planets. Further adjustment brings fainter planets into view. Advanced software processes this data, further improving the contrast and clarity of the image. This processing makes objects more than 1 billion times fainter than the star visible. As a result, WFIRST will provide the first look at individual planets in star systems that might be similar to our own.
So that's how we directly image exoplanets, basically by using magic and technology and all that fun stuff. And I'll be talking about WFIRST, now renamed the Nancy Grace Roman Telescope, in a few slides. But with the direct imaging method, we're actually able to block out that star's light and resolve the light directly emitted or reflected by their host stars. So here is actually an animation of a multi-planet exoplanetary system. And at the very center is where the star is, and the occulter is blocking out the star's light. And what it allows us to do is actually resolve the light emitted from the planets orbiting around its host star. So what you're actually looking at is actually an exoplanetary solar system, where you have 4 planets actually orbiting around their star. And this data set was taken over roughly 7 years, so we can actually watch in real time as the planets orbit around their star in real time. So it's actually really incredible what we're able to do. This method is typically used currently on the ground, but we're now investigating technology to also apply it to space-based platforms. Okay, so now what? We've discovered over 4,000 exoplanets, mostly from the transit method, which has discovered about 3,000 of them. So this is how these 3 methods, as well as some others, are ways we can actually observe and discover exoplanets. So how do we take this next step now from planet detection to planet characterization? Because in order to determine if a planet has life, we need to answer a bunch of questions. Does that planet have an atmosphere? What molecules are present in that planet's atmosphere? Does it have, building blocks for life, or molecules that are required for life, like water, something that's very important for life on the Earth, for example? Then, if that planet has molecules in its atmosphere, could that planet actually then support life? Come on, computer. And then if that planet could support life, it has the right temperature, it has the right molecules, it has water on the surface, it has an atmosphere. Does that planet actually have life on its surface? Just because a planet is capable of supporting life does not guarantee it does have life on its surface. So this takes us to the next step. Determine if a planet can support life. And what's typically used is a metric called the habitable zone. And this is a zone where the liquid water can exist on a planet's surface. And this is important because life, as far as we know it, requires liquid water to survive. So if we look down on the top of our solar system, Mercury and Venus, unfortunately, are a little bit too close to the sun, so they're too hot for water to survive. Mars is just a little bit too far away, but the Earth is just right. It's in the right location, so therefore it has the right temperature where water can survive on its surface. This zone is also sometimes called the Goldilocks zone, because it's not too hot, it's not too cold, it's just the right temperature where water can survive on its surface. And this is why scientists were very excited about the discovery of the TRAPPIST-1 system. This is a 7-planet system with all planets that are roughly the size of the Earth. And 3 of its planets, E, F, and G, are in the habitable zone of the TRAPPIST-1's, its host star. So potentially, planets E, F, and G, one of them could have life on its surface, which is really exciting, is that we might have already discovered a planet that could have life on its surface. But we want to take the next step. We want to go from planet discovery to then determining if that planet's in the habitable zone. But how do we now then say, okay, does this planet have the right constituents, the right molecules in its atmosphere to support life? And a physical law that we use to actually peer into the atmosphere of these exoplanets is called Beer's law. So here's the definition of Beer's law. This is studying for a test or doing homework while Beer is involved, making difficult classes such as physical chemistry more bearable. That's a good Beer's law. It's not the one I'm thinking about. Here's the one I'm thinking about, sorry. This is Beer's law. What it does is it describes the absorption and scattering of light out of a beam. So for example, if we have a light bulb on the left and we shine it through a chamber of gas, that light bulb will look a little bit dimmer. And if we look at how the light from that light bulb is absorbed as a function of wavelength by looking at its spectrum, we can actually back out the composition of the medium that is doing the absorbing. So if I put a light bulb on the left, it shines through a chamber of methane gas, for example. Methane will absorb light at certain wavelengths, and that pattern of the spectrum will allow me to then directly say this planet has methane in its atmosphere. So Beer's law describes the absorption and scattering of light out of a beam. So if we observe, for example, a yellow star, you would expect that star to look yellow, right? But if there's a cloud of gas and dust in the way, the gas and dust cloud will absorb the light from the yellow star and actually cause it to look a little bit more red. So if we observe what an object does look like and compare it to what it should look like, we can then determine the composition of the absorber directly with Beer's law. And then we can say, hey, that cloud actually has molecules in it, and actually then determine what are the actual molecules that are in that cloud. We can also use this for exoplanets. So a lot of exoplanets that we're discovering are large planets that are also very young. Since they're young, they're hot and they're bright, they emit a lot of light, so they're easier to see, they're easier to discover. And these planets have leftover heat trapped in their cores from when they formed. And these cores are radiating that heat away. And as that heat goes through the outer layers of the planet, those outer layers are comparatively cooler. So the planet's own atmosphere absorbs the light and the heat emitted by the core of the exoplanet. So that light and heat might have originally been yellow. By the time it escapes the planet's atmosphere, it's now red. And then astronomers can look at that light and then infer that that planet, for example, has methane in its atmosphere. We can use the same technique to actually look at scattered or reflected light. So if a star, like our own sun, is emitting yellow light, that light hits Jupiter's surface, and that light is reflected by Jupiter's clouds as red light. And then astronomers can say, hey, that planet has clouds on its surface. So we can actually directly characterize an exoplanet just by looking at its light. And that's really helpful because these planets are hundreds upon millions of miles away from us. And despite that, we can use the transit method, the direct imaging method as well, to characterize the composition of these targets just by looking at their light. So here's actually a few exoplanet spectra. So on this axis, I have a bunch of different exoplanets ranging in hotness. So the planets at the top are very hot, the planets at the bottom are relatively cool. On this axis, this is the flux offset. So again, bright is towards the top, bright and hot is towards the top, cool and dim is towards the bottom. And then on this axis is the wavelength of these exoplanets. So what we're observing is actually 9 directly imaged exoplanets. And this is light emitted from their hot young cores that's then being absorbed by their relatively cooler atmosphere. And this causes bumps and wiggles to occur in the spectrum of these exoplanets. And at these wavelengths, if I see a bump and wiggle here, I know that planet has water in its atmosphere. If I see a bump and wiggle at these passbands, I can infer that that planet has methane in its atmosphere. At this wavelength is where carbon monoxide, for example, very strongly absorbs light. So if I see a bump here, I can infer that planet has carbon monoxide. So some of you eagle-eyed observers out there might be seeing these gaps in the data. So the reason for these gaps in the data is actually these were observations all taken from a ground-based telescope. And this is where the absorption bands of the Earth get in the way. So the Earth actually absorbs light, due to really annoying things like water and oxygen, annoying stuff. And the water in the Earth's atmosphere actually strongly absorbs light at these wavelengths. So if I wanted to look at these wavelengths of light using a telescope, well, what do I have to do? I have to launch that telescope up into space. So this is why space-based observing is very, very crucial for understanding the universe, because it allows us to peer above the absorbing layers of the Earth's atmosphere and actually unlock the information at alternate wavelengths that were not really available to us on the ground. So the Hubble Space Telescope has used this method very successfully to observe the atmospheres of transiting exoplanets. It has an instrument on board called the WEBB-C3, it's the Wide Field Camera 3, and it observes light across a wavelength band that I'm showing there on the right in blue. And this wavelength band happens to match up very well with where water strongly absorbs. So this is why, if you've been noticing, a lot of press releases on exoplanets are about whether or not water exists or doesn't exist in that planet's atmosphere. And that's largely because we're biased by our instrumentation. Hubble has this passband that is most finely tuned to finding water on the atmospheres of these planets. In the future, though, future missions such as the James Webb Space Telescope will be able to look outside this water band and be able to look for evidence for the existence of other molecules such as methane, carbon dioxide, and carbon monoxide. But Hubble has been finding water on almost every single planet it's been looking at. So on the right is a 30-planet sample where it's actually Hubble's been mapping out the existence of water vapor across many different planets. And we're finding that water is actually ubiquitous on exoplanetary atmospheres. So that's great. Water is required for life on Earth. If water is out there on many exoplanets, it might mean that life is also elsewhere outside of our solar system. Unfortunately, the planets we're looking at today are typically way too hot and way too big for life to survive on their surface. These planets are so hot that water actually exists in the gaseous form in their atmospheres. But these methods that we're using to look at planets that are large and hot and bright, these are the same methods we'll be using to look at smaller planets that could potentially have life on their surface. And we'll potentially be doing these observations with the James Webb Space Telescope. This is an absolutely massive telescope. It's actually being tested right now just south of LAX. I'm really fortunate I got to see it myself. It's pretty cool. That bottom purple thing is its solar sail that blocks out light from the sun, solar sunshade, sorry. And that's about the size of a tennis court. The golden mirror there is about 6 meters across. So it's a very, very large piece of spacecraft. It's incredible. Another instrument that we'll be using, another telescope we'll be using to observe exoplanets is the Roman Space Telescope. This is formerly WFIRST. This is the mission referenced in that video I showed you. And this is actually a mission I work on at JPL. And I'm part of the project science team that is trying to make sure that one of its instruments called CGI, the coronagraphic instrument, will be operating correctly and sufficiently to directly image the light of exoplanets. And this will be launching sometime in 2025 or 2026. So Roman CGI is basically, it's a stepping stool or a stepping stone. It's a technology demonstration to demonstrating that this technology of directly imaging exoplanets can be carried out in space. Currently, most direct imaging observations come from large ground-based telescopes. And these large ground-based telescopes are typically looking at infrared wavelengths, and they're observing hot superjupiters, large planets that are bright and hot and therefore easier to see. What CGI will do is it'll start to push that boundary a little bit closer and to cooler planets. So it'll be operating at visible and near IR wavelengths, and it'll actually be able, for the first time, be able to observe true Jupiter analogs, Jupiter-like planets orbiting solar-type stars. And this stepping stone is absolutely crucial for enabling the science of future missions. So future missions want to find life around on planets orbiting around their star, on Earth-like planets orbiting these stars. But those planets are small and very close to their stars comparatively. So CGI provides that stepping stone from where we are to where we want to be. So there's a question, space-based observations, you don't have to worry about the Earth's atmosphere. You can look outside these absorption bands from the Earth's atmosphere. So why even bother with the ground, right? Space-based telescopes are not limited by Earth absorption. They're minimally impacted by sunlight. However, there's very few space telescopes. So we're limited both in available time and also wavelength space. Ground-based telescopes, on the other hand, allow us, there are a multitude of telescopes around the world. So there's numerous platforms and many different instruments. However, again, the Earth's atmosphere gets in the way, and you can actually have large systematic errors that can be induced as the telescope slews around the sky. But given this we've developed and are testing an instrument actually at Palomar Observatory called NESSI, the New Mexico Exoplanet Spectroscopic Survey Instrument. And NESSI is actually right now in the ELAB, electronics lab at Palomar, in the 200-inch Hale telescopes inside the building right now. And we've been commissioning it over the last year or two to actually perform a survey of exoplanets, to characterize their atmospheres and look into the composition of those exoplanetary atmospheres. So right here, here's a picture of NESSI in the ELAB at Palomar. No, that's a mythical sea creature. Sorry guys, 1 second. All right, here's an actual picture of NESSI in the ELAB. The instrument's the center, it's the blue thing. On its handling cart, that silver thing. And at the bottom are some of its hardware. And then I'm actually doing some testing of NESSI and filling with liquid nitrogen. So here's some photos actually of NESSI. We did a lift test and a lift check. There's the instrument principal investigator, PI, Michelle Creech-Ekman. I love her shirt. It says, "I want to believe," and has a picture of NESSI on there. My boss at JPL, Mark Swain's taking a cool photo and ignoring me like usual. But NESSI, what it does is it sits at the secondary in the prime focus cage of Palomar's telescopes. Normally on a telescope, you think of light coming down, hitting the primary mirror, and reflecting up to a secondary, where it's then reflected again back down to the instrumentation at the bottom. NESSI actually sits at the very top of Palomar in the prime focus cage. And this is to maintain its wide field of view. So how do we get NESSI from the ground all the way up above to the prime focus cage? Well, you crane it up there. Right about now, we're hoping our insurance policy had started for NESSI. Luckily, it did. And now I'm getting anxious as NESSI's wheeled over a very historic 200-inch mirror. But luckily, NESSI made it, and it actually fit inside the prime focus cage. So this is a picture of my boss, Mark, smiling and laughing because we got everything installed and NESSI was working great. He's also laughing at me because I am definitely afraid of heights. But as the JPL commissioning lead on NESSI, I have the pleasure of having to go up to the prime focus cage. So it's always a terrifying experience for me. But despite that, we get some really cool photos up there. So there's NESSI nestled nicely at the prime focus cage at the 200-inch telescope. And we've actually been able to observe our first transit with NESSI. And from this light curve, we were able to estimate that due to the large primary mirror Palomar and due to our instrument, that we're actually able to get very close to the same precision that the Hubble Space Telescope has, which is absolutely incredible. So this is how, by using transit spectroscopy, by using Beer's law, by using direct imaging, this is how we can actually look into the chemical makeup of these exoplanets, see if it has the molecules that are necessary for life to survive. But then you have to, again, take that next step. Just because a planet could support life doesn't mean it actually has life on its surface. So how do we find life? Well, we can do a little thought experiment. We can launch a satellite and turn it around as it's cruising out into the solar system, turn it around and have it take a photo of the Earth. And we can analyze the light reflected or emitted or absorbed by that planet using Beer's law to look for the bumps and wiggles in the spectrum of that exoplanet, to look for life, to look for evidence of oxygen produced by plants and algae. We could look for liquid water on its surface. You could also look for signs of biological activity like cow farts, right, or methane. But the crucial thing is you have to rule out all other explanations. We're finding methane, we're finding water right now on exoplanets, but these planets are too large, too hot for life to survive and exist. And this is why a lot of people are spending a lot of time looking into things called biosignatures. These are bumps and wiggles in the spectrum of exoplanets that indicate that life exists on their surface, because otherwise, those bumps and wiggles, those spectroscopic signals, could only be formed and created by life on their surface. Another way is we can actually talk to life directly. So, for example, in Voyager 1 and 2 were launched by JPL in 1977, did this grand tour of the solar system. And they each had a golden record on board that actually had recordings of various greetings and from humans on Earth, and also sounds of Earth, and also a bunch of images. So there's a picture of the golden record on the right. We can also send messages directly to aliens, for example. So SETI, the search for extraterrestrial intelligence. Back in the 70s, Frank Drake and Carl Sagan actually wrote a message to aliens using Arecibo. This was the world's largest radio telescope at the time. So large, it actually fits in the valley between some mountains in Puerto Rico. And they sent a message out to a globular cluster, a patch of stars orbiting around the center of our galaxy. It's a very, very dense patch of stars. And they sent that message on the right. At the top in white is demonstrating that we know how to count, always a good thing. Below that are a bunch of molecules and atoms. The red thing in the center is a human. The double helix above the human is DNA. The thing in purple at the bottom is actually Arecibo. And then the picture in yellow is actually our own solar system. So there's the sun, Mercury, Venus, Earth is elevated because that's where we're from, Mars, Jupiter, Saturn, Uranus, and Neptune. And since this was in 1974, they didn't know any better and they thought Pluto is a planet. So they actually accidentally included it there. But now we know better. Pluto is not a planet. So this message to aliens is saying, hey guys, we're humans, we know how to count, we know about atoms and molecules and stuff, we know about DNA, we think we're pretty smart, this is how we sent our message, this is where we live, please come and enslave our entire human race, right? Luckily, M13, the globular cluster they sent the message to, it's very unlikely that planets exist in that globular cluster. The stars are so tightly packed that any planets forming in there are actually ejected away from the globular cluster. So we can breathe a sigh of relief. We dodged the bullet there, guys. Don't worry about it. It actually wasn't until very recently that an exoplanet was discovered in a globular cluster. So it's very rare that they form there. Another way is we can send messages, such as from social media, because nothing bad happens on the internet, right? So back in 2008, 501 messages were sent to a system called Gliese 581c. Because this system, both planets C and D are potentially in the habitable zone of this host star. So life might exist on that star's surface, on those planets' surfaces, sorry. So these messages will arrive in 2029 because this planet is about 20 light years away. And if aliens, if they live there and they're able to communicate, send a message immediately back, we'll hear a reply in 2049. Which is pretty cool to think about. So the question is, where are we now? And unfortunately, despite what the History Channel might say, we have yet to make any conclusive detection about extraterrestrial life. And the question is why? Why haven't we found life? If planets are everywhere, and if they're very numerous, and then implying that life might be very numerous, well, maybe our technology isn't good enough. Maybe the signal is very small, and we just don't have the signals noise necessary yet to be able to detect the signal from aliens from life. Alternatively, maybe we just haven't found them yet. Maybe they've been talking from the left, we've always been looking to the right. Jill Tarter, who's the scientist that was the inspiration for the movie and the book Contact by Carl Sagan, gave a really great analogy. If we take all of the universe and we shrink it down into the size of the Earth's oceans, despite how much we think we've discovered and understand about the universe, in total, we've actually only explored the equivalent of a cup of water's worth. So there's much more for us to explore and discover and understand in the universe. Or maybe most depressingly, maybe we are absolutely all alone, which is pretty depressing. So on that very high note, I will say thank you so much, and I'll be happy to take any of your questions. Thank you.
Rob, thank you very much. Let me remind everybody that if you want to ask a question, you need to turn your microphones back on. If I may, let me start with a question. In terms of characterizing exoplanets, here they've added a polarimeter and upgraded the polarimeter on wide field infrared camera. Are there polarimetric techniques for characterizing exoplanets?
Yeah, so the group at Caltech that typically operates WORK and WORK-POL, they use the polarimetry to look at the polarized light typically reflected by the atmosphere, the clouds of these exoplanets. So polarimetry actually allows us to sort of peer into the composition of the clouds of these planets. And actually the composition of the clouds of these planets is actually one of the biggest mysteries still, unresolved questions in exoplanet science. While we can observe exoplanets, we can observe that they have clouds in their atmosphere, we still don't know what those clouds are made up of. And yeah, WORK-POL can actually be used and is being used right now to sort of peer into the composition of those.
And if I could use that as a segue into presentation two weeks from now, Gao Tinanot will be talking about some of that in 2 weeks. Okay. Other questions?
Looks like we have one in the chat from Alan. So he's asking, why do we need a large field of view for looking at the intensity variations of a single star? And the reason for that is a wide field of view allows us to look at a comparison star. So just like with multi-object photometry, if you have a comp star nearby your target star, you know your comparison star, its light should be flat at the end of the day. If you remove systematic error effects, like the rising and setting of the telescope as it traces the rising and setting of the star, if you are able to divide that out and make it flat, those systematic error corrections that you make for your comparison star, you can also do the same corrections for your target star. So just like multi-object photometry, we do multi-object spectroscopy of NESSI. So if we have a spectrum of a nearby comp star, we can use that to map out our systematic errors and apply that same correction to our target star. And then to answer Mark's question in the chat, I'd be very happy to do a remote talk like this to your TVA club, Mark. So feel free to get in touch if you want me to do that. Or I'm also happy to wait until we can finally see each other in person and give it the talk in person as well.
I've got a question.
Yeah.
What about interferometry? You know, when you talk ground base, how about interferometry?
Yeah, so interferometry is typically currently being used for resolving the disks of stars. So an interferometer here actually in LA, here actually relative to me, there's one run by Georgia State University at Tabletop Mountain right by Mount Wilson. And they're actually able to take really high spatial resolution images that can actually resolve and see directly the disk of those stars. I think they're able to do that for like Betelgeuse, for example, which is pretty incredible. I don't believe we have the power yet to use interferometry to look at exoplanets, but potentially that could be a method used in the future.
Okay. Well, we got another question.
Sure.
You know, last day or two, there was a article that came out about photographing two large planets around, I don't know the name of the star.
Yeah.
Is that an example of what you're saying can be done rather typically, I guess?
Yeah, so that was a big breakthrough because it's the first time we observed planets around a solar type star, and I believe they were relatively small planets, which is pretty exciting. And yeah, that's the direct imaging method. So that's typically done with larger telescopes on the ground, about 8 to 10 meter class telescopes at least, typically. Palomar also does direct imaging measurements as well on the 5 meter. I forget the instrument on Palomar, unfortunately, but they are able to do direct imaging measurements of exoplanet systems. The Roman Space Telescope, which will be launching in a few years, will also be using the direct imaging method to block out the light from the star, allowing you to resolve the small light emitted or reflected by that planet's atmosphere.
Okay. Follow-up question on that.
Yeah.
Was that picture because the relative positioning between us here on Earth and that star, and that we're really looking like from the north, from north to south on that star's planetary system?
Yeah, so if the planets get too close to their star, they're going to be obscured by the light emitted by the star. So that's why it's always easier to find planets that are big, bright, but also far away from their star. Because if you occult the light from the star using your coronagraph, you're also potentially likely going to block up the light emitted or reflected by the planets within that little ring. So it's easier to find a planet way out here than it is way in here. But since Roman will be operating in space, we can have better control over how we block out the star's light, and we can actually start looking for planets that are dimmer, but also closer to their host star.
So does it matter that the planets are in a horizontal effect as opposed to a vertical?
In the sense of their distance from the star matters more. So you can actually observe directly imaged planets regardless of their orientation or their inclination relative to us. But if they're too close to their star, then the star's light will overwhelm the signal and we won't be able to directly image them.
Oh, okay. Thank you.
Yep.
So this is Antonio. Thank you for the talk. I have some vague memory of somebody assembling a bank of DSLR cameras to observe the sky in New Mexico. I don't know if any of that is useful or even viable.
Yeah, so people use DSLR cameras to observe the entire night sky, and they can observe transits that way. People are also using smaller telescopes as well. So M-Earth, it's the M-Earth project. They've actually been able to discover a bunch of exoplanets using small telescopes. There's the KELP program, there's the EXO program, there's a bunch, TRESS, there's a bunch of different ground-based surveys that are using small telescopes to discover exoplanets. With our project Exoplanet Watch, we want to have amateur astronomers, such as some people on this call, to use their own system or data taken by a remotely robotic telescope to follow up these transiting exoplanets, to update their transit times to make to ensure that we use these large observatories more efficiently.
And a completely different question.
Mm-hmm.
I'm not exactly clear, but I think planets are brighter in infrared, whereas the stars are brighter in optical. Does that help at all?
It's about the peak of the brightness. Yeah. So
Yeah.
stars emit most of their light, typically solar type stars emit most of their light in the visible. And that's why our eyes are actually tuned to the wavelengths of light that we see, because that when we're evolving and forming and our eyes are forming, they matched up with the peak intensity output from our own sun. Exoplanets, since they're a little bit cooler typically than their host star, their black body spectrum is shifted to longer wavelengths. So the flux ratio is maximized in the infrared than in the visible. But the planets are still much, much, much dimmer than their host star at all wavelengths.
Oh,
It's just the flux ratio is a little bit better in the infrared than it is in the visible.
so the difference is the star is still far brighter in infrared than the planet.
Yes.
But not by as much, but still.
Yes.
Okay.
Yep, exactly.
Oh, well. Thank you.
I have a question. You showed a diagram of an advanced coronagraph. Can you say anything about the stellar double coronagraph or the super duper at Palomar?
I actually don't know a lot about that one, unfortunately. My background is mostly transiting exoplanet observations, and I just recently got into direct imaging about a year and a half ago when I joined the Roman Space Telescope CGI team. So I only really know about a little bit about work because I've just been hearing about it, and mostly about NESSI because that's what I spend all my time at Palomar doing. So when I'm at Palomar, I'm usually kept pretty busy and working mostly on NESSI, so I can't, unfortunately.
Another question, and it occurred to me when I saw your diagram of Roman. Remember 3 years ago, maybe a little bit longer, the NRO had some extra surveillance satellites and they were going to make them available to NASA if NASA could reconfigure and use them. Was that ever taken advantage of?
Yeah, that's actually what Roman is. So Roman is actually literally that spy satellite telescope, and we've now reconnoitered it from, instead of looking down at the Earth, we're now pointing away into space. So that Roman is actually one of those telescopes.
Oh.
Yep.
Thanks.
No worries.
Other things, other questions? Rob, one thing I thought while you're going through, you know, talked about discovering exoplanets and using direct imaging. Isn't it the case that really very few exoplanets have been found by direct imaging?
Yeah, a handful of them, about 10 to 20, have been found with the direct imaging method. Actually, Vanessa Bailey, who's actually the technologist of CGI, a friend of mine, we actually went to graduate school together. She actually discovered one of them, and another one of our project science team members, Tiffany Meshkat at IPAC, discovered them as well. So it's pretty cool that they've discovered between them about 10% of all directly imaged exoplanets. So the question is, if exoplanets are everywhere, if they're ubiquitous, why have we only discovered a very few with the direct imaging method? So what I think is happening is that the planets are there. They're just so dim and so close to their host star. They're very difficult to observe and discover with current technology. So one of the things we're hoping to do with the Roman Space Telescope with CGI is, if we're granted an extended mission, is actually we can do a blind search and try to discover additional exoplanets that are cooler and dimmer and closer to their star, and perhaps more numerous and more likely to be discovered as well.
Question.
Yeah.
If you, you know, when a planet, exoplanet is found by one person, someone has to confirm that finding, correct?
Mm-hmm.
All right. If you photograph a planet, do you have to have it confirmed?
You have to confirm it as well, in the sense that you have to prove that it's not like a background star. So in that recent press release, if you saw the photo, there's the 2 planets at the bottom. There's also, I think, 3 stars nearby in the background. So you have to do a lot of reconnaissance to confirm that the little thing of light that you're seeing is actually a planet dynamically tied, gravitationally tied to that host star, as opposed to just maybe some background star that's sort of moving through the field of view. So a lot of work is actually needed to confirm. You just can't take a photo, unfortunately. You actually have to do a lot of background work as well.
It could be self-confirmed then by the same observer.
So the transit method, if you're talking about observing or discovering a planet, you have to, it doesn't have to be an external group that can do the confirmation. One whole paper, one whole study can do the confirmation as well.
Okay.
So it depends on how the planet is discovered. With TESS, for example, it publishes a bunch of candidate planets. And then people will then use other detection techniques or other observational methods that are complementary to the transit method to confirm that exoplanet. And the same thing happens with direct imaging as well. It doesn't have to be, again, an external group. It can be all the same research team that is characterizing that planet and confirming it as well.
You just have to try to do it like a different technique to confirm.
Yeah, it sort of depends on the method that you're using to originally discover it. So you can use a different technique, or you can use statistics, or you can use different observations to help confirm that planet as well.
Okay, thank you.
Yeah.
Other questions? Rob, really, thank you very much. It's a great presentation.
Yeah, thank you so much for having me. Appreciate it. And a big thank you again to Scott. Thanks for calling in and for sticking through my talk, but also getting us data for that publication. Really appreciate your help with that.
Well, it's impressive that, you know, people can help and participate in that that way. I think that's just a very, very cool thing.
Yeah. So again,
Rob,
if you're
Rob,
oh, go ahead. Yeah.
I was just going to say you're very welcome, and I've certainly enjoyed it. And we now have the Terra Observatory working pretty well at our site down here in San Diego, and we've got a few new observations we're going to share with you very shortly.
Awesome. I look forward to seeing them on our Slack channel. Thank you. Yeah, so if you're interested in participating in this project, please reach out to us, exoplanetwatch@jpl.nasa.gov, and we'll probably get back to you on Monday because we want to take off the weekend. So, but yeah, also go to our website, please. That'd be a lot of fun. And everyone is welcome. Regardless of the size of the telescope, we think that we can actually do these observations with a 3-inch telescope, which would be cool to see. Wow. But again, if you can do astrophotography, transiting exoplanet observations by comparison are infinitely easier. You don't need precise tracking. You just don't have to, just don't saturate in your target star. That's basically it. And if you do take astrophotography, please post them to our Slack channel because I love looking at all your awesome, pretty photos as well.
If again, any other questions or comments or whatever? Let's.
Sure. So I'm trying to figure out, at some point I heard some statistic like almost every star has at least one planet, or does that make sense, or? Yeah.
So Kepler allowed us to determine that for there's as many planets as there are stars in the sky. Not necessarily every single star has a planet, but the planets are at least as numerous as stars are, if not more numerous.
So would certain stars be more likely or less likely depending on their size, intensity, or allow planet formation or not, or?
I believe generally the smaller mass stars are more likely to have planets. So MGK type planets or stars are more likely to have planets than OB type stars.
Okay. And I once attended some lecture that was saying that most planets, we have observational bias, but most planets tend to be like Neptune size, or is that? Or do we know so far?
Yeah, so far, typically we're finding larger planets because they're easier to find. are also thinking that large super Earth or mini Neptune type planets are more likely, but
Yeah.
but it's just a matter of time until we start discovering more Earth-sized objects.
Okay.
And these Earth-sized objects will be and are being discovered right now with TESS. So that's another crucial reason why TESS was launched, is to identify small planets around end-dwarf stars that can then be followed up by missions like James Webb or Ariel or other future missions as well.
Okay.
Mm-hmm.
Thank you.
No worries.
Rob, is anybody talking about using transit method to look for exoplanets in the Andromeda galaxy or M33 or other? I mean, is that in the realm of possibility?
I think they have discovered an exoplanet in Andromeda. I forget. Most of the planets we're discovering, though, are within our own Milky Way because, if not all of them are in the Milky Way. Otherwise, the stars are too far away. They're too dim. It's harder to resolve them. But I believe they might have used the microlensing technique to discover a planet in Andromeda. I need to double check that, though.
Cool.
But yeah, they could be there.
Again, Rob, thank you.
No worries.
2 weeks from now, Al Tynanot will talk about polarimetry. He just recently finished the defense of his thesis and is a newly minted Caltech PhD. And he did most of his, not most, he did a great deal of the research for his PhD here at Palomar. So he's going to talk about what that was all about. I think it'd be a very interesting discussion. Anyway, with that, I think time to shut this meeting down. I thank everybody for coming. Please come in 2 weeks, and we'll see you all later.
Thank you again, everyone, for having me. Really appreciate it, and hopefully I'll see some of you guys at Palomar in person not too soon, or not too.
When it works. Yeah, thank you.
Exactly. Thanks, guys. Have a good one.
Great talk,
Bye.
Rob.
Thank
Great
you.
talk, Rob.
Super.
Thank you.